So now we're going to go to the charged plate. So basically we want to find out what is the electric field of a charged plate, the distance x away, and the radius of the plate is r. First I'll do uniform charge density to non-uniform charge density. So what we are going to do is use the result that we obtained from the ring problem when it was a ring. So the plate is made up of a bunch of rings. Right? So take a little ring like this, and we say the electric field of a ring, a distance x away, and the radius of the ring is r. Remember, we found out that the electric field was kq x over x squared plus r squared to the 3/2 power. Right? So now, what is going to happen? Well, in our case, each of the rings composing that plate will produce their own electric field to the right if the charge is positive, and they will all add up. So this is going to be dE. dE. The electric field produced by one of those rings is dE k, and then over here I'll put kx dq over x squared plus r squared 3/2 power. Now r squared will be what? The radius of that particular ring. And the radius of each ring is changing, right? There are small rings, big rings, and then as you go towards the outside, the ring gets even bigger, right? So the radius is not constant, okay? So you have here r squared. So now what am I going to say? Well, I'm going to say dq is the surface charge density sigma times the surface area of this dA, and dA is equal to what? 2 pi r dr. Okay, it's the circumference of a circle times the thickness of the ring, dr. So you put that over here, and you get dE is equal to kx over x squared plus r squared to the 3/2 power. dq is 2 pi r sigma dr. Now we integrate this from 0 to capital R. Okay, the radius of the charged plate. So we're going to integrate. Now what is constant, what is not constant? Well, as I go from one ring to the other ring, see these are the rings here. These are the rings. The distance x is staying the same. X is not changing. So I don't need to integrate x. R, the little r is changing, right? The little r is the radius of the ring. So the only thing that I'm integrating here is over dr, right? The radius r is the what's changing as a function of the different rings. So the total electric field, all of these other things can come out. 2 pi k sigma x, 2 pi k sigma x, and then all that's left is r dr over x squared plus r squared to the 3/2 from 0 to capital R. Okay, now this is actually an integral that's easily doable by u substitution. Let u equal x squared plus r squared. du is equal to 2r dr, right? Therefore, r dr is therefore r dr is equal to du over 2. Okay, so over 2 over u to the 3/2, and then if I just focus on the integral for a second, you're going to have here the 2 is going to come out. Let's just do the integral here, 1/2, and then you're going to have integral u to the minus 3/2 du, and then the integral of that is you add 1 and you add 1, so u to the 1/2 u to the minus 1/2, right? Over minus 1/2. Minus 1/2. Well, actually what ends up happening, the 2 and the 2 cancel, and then this becomes negative 1 over u to the 1/2. And now I can put down what u is, x squared plus r squared, right? To the 1/2 power from 0 to r. Now I can put the limits of the variable. Remember, the x is not the thing that you are integrating, it's the little r. So the big R goes into the little r, and then a 0 goes into the little r. So this one goes in here. You have minus 1 over x squared plus r squared to the 1/2 power, minus negative 1 over, then you put in 0, x squared to the 1/2 is just x. So this one becomes a positive. Now I can bring this in, and I can say E total is equal to 2 pi k sigma x multiplied, rewrite this as 1 over x minus 1 over x squared plus r squared to the 1/2 power. And if I want, I can multiply the x in there, right? Distribute the x, and you end up getting 1 minus x over x squared plus r squared to the 1/2 power. And I can finally put in what the sigma is. In our case, the sigma was a uniform charge density. So sigma is going to equal q over pi r squared. So q over pi r squared. And then the pi and the pi will cancel. Okay, there was already a pi there. So basically the final answer is 2kq over r squared and 1 minus x over x squared plus r squared to the 1/2. Now if I want to find the electrical force on a charge, then I just multiply this by the charge of that other charge, little q. Okay, so now let's find the limit of this as x goes to 0, as x goes to infinity. Limit as x goes to 0 of the electric field, 2kq over r squared, 1 minus, and again this one becomes just x, and then when x is 0 it becomes negligible compared to that, so it basically is going to have x over r, 1 minus x over r. So the electric field right at the center is equal to what? When x is equal to 0, it's going to be 2kq over r squared, if I distribute this in, minus 2kqx over r cubed. Okay, so the electric field of a disk at the center, it starts out as 2kq over r squared, and then it drops off linearly when x is a small number, right? So it has that linear behavior. So if you notice, this is similar to the linear behavior that the ring displayed. For the ring, the electric field when x was 0, it was kq x over r cubed, okay? Near the center of the ring. Here you have 2kq over r cubed x. So it's double that, right? And there is this constant term. So that means even when the x is 0, there is still an electric field due to the plate. Well, that's because the plate is made up of a bunch of rings, right? So you basically have a ring here, a ring here, a ring here, a ring here, a ring here. For the ring, for a single ring, the electric field configuration looks like this. It kind of diverges out, right, on both sides. So the electric field at the center is very, very weak, you see? And when you're exactly at the center, the electric field is 0 because the two electric fields come and meet and you basically are equidistant from the whole ring. But when you have a bunch of rings, what's going to happen? When you have a bunch of rings like this, like this, like this, like this, those electric field divergence is going to be straightened out, and you're going to end up with electric field like this. And it's only going to diverge towards the ends, okay? Or as you go out very far away, right? Like this. So basically the effect of having a bunch of rings is to straighten down the electric field and to make the electric field have a certain value even when you're at the center of the disk, okay? 2kq over r squared, and then it drops off as 2kq over r cubed x, double the value of the behavior of a single ring, okay? Now, if you notice something, we could also express this a different way. We can say sigma is equal to Q over pi r squared, and Q is equal to sigma pi r squared. So we could take wherever we're seeing a Q, we can replace it by this value, 2k over r squared. Q is going to equal sigma pi r squared. Let's actually just focus for a second just on this value here, not the behavior as a function of x. So if you rewrite this, you have the limit as x goes to 0. The r squared cancel. You have 2k sigma pi, right? And then the radius of the disk canceled out, and I have it expressed in terms of the charge density. Now I can put down what the k is. Remember, k is equal to 1 over 4 pi E0. Okay, the electrical permittivity. So I could put that in here. I have 1 over 4 pi E0 sigma pi, and then over 2E0. Okay? If you remember, using Gauss's law in chapter 24, we could derive the equation for the electric field of a disk. So you draw a Gaussian, cylindrical Gaussian surface, and it's very easy to derive. If you can assume that the electric field is not diverging out at all, the electric field only goes this way and this way, so you have EA to EA, right? The EA here, and the total flux is equal to the charge enclosed over E0, right? And the electric field is equal to Q over A is the sigma over 2E0. Therefore, we got the same result doing all of this integration, finding the limit as x goes to 0, sigma over 2E0, we got the same result as we got when we applied Gauss's law to a plate, assuming there's no divergence of the electric field, right? So it's a very interesting result. What would be the behavior of that electric field as x goes to infinity? So what is the limit of this as x goes to infinity? Well, that one, when x goes to infinity, this one is going to be what? Say you have x and then r squared is negligible compared to this. You have x and you have x squared to the 1/2, so you have x. It cancels itself out. So another technique that we can use to find the limit of this as x goes to infinity, we use a binomial expansion, 1 plus x to the power n, and we have 1 plus nx plus n times n minus 1 over 2 factorial x squared, and so on and so on and so on. So whenever we want to find out the behavior of something, one way we could do it is we can say if x is much, much, much less than 1, the terms x squared, x cubed, x to the 4th are going to be negligible compared to the term x. So we don't even have to worry about that. So 1 plus x to the n is approximately equal to 1 plus nx if x is a small number, right? So how could I rewrite this here? Well, I could rewrite this as 2 pi k sigma 1 minus x squared plus r squared to the negative 1/2 power, right? And what I could do is I could take out an x squared from there, right? That's x, and then I take out an x squared, and then I have 1 plus r squared over x squared to the negative 1/2 power. Okay, so basically you are taking an x squared out of here. X squared is also raised to the power negative 1/2 power, and all of this is raised to the negative 1/2 power. But when you do x squared to the negative 1/2 power, what do you get? Well, you just get x to the negative 1. So this comes out of that, and you end up with x to the negative 1 on the bottom, and then it cancels out with this, and essentially you only get this now. Okay, so by taking out an x squared, I was able to get rid of the x here, and I have a clean 1 plus x to the nth power looking thing, right? So I have E equals 2 pi k sigma 1 minus 1 plus r squared over x squared to the negative 1/2 power, right? Now I can say this is equal to 1 plus nx. Okay? 1 plus, and then n is negative half, and then x is itself, r squared over x squared. And then higher powers of this are going to be even smaller because x is going to infinity. So I don't need r to the fourth, x to the fourth, r to the sixth, x to the sixth, and so on, right? 1 power is enough. So I can keep it at that. And 1 minus 1, it's going to cancel, minus negative, and therefore only this will survive. This one and this one will cancel. And you will end up with what? Minus and minus, negative, that's going to be a half r squared over x squared. Okay? Notice what's going to happen now. The 2 and the 2 cancels. Pi k, and then the sigma is the charge of the plate over the surface area of the plate times r squared over x squared. Okay? Notice what happens. Pi cancels, r squared cancels, kq over x squared. Wonderful! The behavior of the electric field of a charged plate, when you go infinitely far away from it, the plate begins looking like a point charge, and the electric field resembles that of a point charge. Okay? So now let's see what happens if the surface charge density of the plate is not constant. Okay? Next we will go to that.